Hi, my name is José Pombal, and I'll be presenting Prisoners of Their Own Devices, How Models Induce Data Bias in Performative Prediction. So the main motivation for this work is that machine learning models have the potential to exacerbate existing social inequities because of discriminatory predictions that they might make. And most works in FairML only focus on measuring unfairness in static environments, even though most real-world applications actually operate in dynamic environments. For example, fraud detection, where fraudsters are constantly adapting to the behavior of fraud models to avoid being detected, which results in changes in the data's distribution. So in these cases, it's actually the model behavior that's influencing changes in distribution and its biases, which might result in future unfairness. So we need to find a way of reasoning about what types of biases arise in these circumstances and the effects that they have on fairness accuracy trade-offs or fairness that models exhibit downstream. So the first contribution we make is that taxonomy to characterize data bias between a predicted attribute, other features in the target. And then we model two settings where data bias is induced by the predictive model itself, like in performative prediction, and show the detrimental consequences that this has on performance and fairness. Our taxonomy starts with a base condition that states that data is biased if the predicted attribute is related to either the features, the target, or both, which unfolds in the group-wise class conditional distribution, which pertains to the features, noisy labels, which pertains to some observations being incorrectly labeled, and dynamic bias, which states that the biases we find in training might be very different from the ones in production. This underlying assumption here is that as the data's distribution changes across time, so might its biases. So we have to take this into account. The first scenario that we model is adaptive fraudsters. And fraud detection is strategic because, like I said, fraudsters adapt to the predictive model, which changes the distribution in the data. And we find that the consequences of this, so if we train and test models on a scenario where there is no adaptation between training and testing, and a scenario where there is adaptation, and so some features become useless, we see that there is a substantial decrease in both performance and fairness of models. And we also see the best models before adaptation are not the ones after adaptation, so we might be choosing the wrong models for production. And that actually fairness-aware models might be good for these types of scenarios, especially if this adaptation results in some change in the relationship between the features and the predicted attribute. Our second scenario relates to noisy labels, selective noisy labels. And fraud labels are selective because to reject an account means that we'll never get to observe its true label because the account never materializes. So we never get to know if it was actually going to be fraud or not. But a common practice is to assume that all these observations are label positives. And then we train future models on the data that we obtained in the past, and some of these observations will be wrongfully labeled because for sure we'll have some false positives. And we ask the question, what are the consequences of this assumption on false positive rate across time? And for banks, false positive rate is a proxy for customer attrition because each false positive is an angry customer that might want to change banks. So we want to keep this at a certain level. What is the consequence of this level in production? We find that the level that we think we're practicing in the validation set, which might be, for example, 5%, it's in this case, as noise levels increase across time, the FPR level in production becomes very different from the one we think we're practicing. In particular, it increases because the models are training on wrong data. We also tried a fairness intervention, and we find that the effectiveness of the intervention actually also decreases as noise level increases. So the main conclusion here is that both FPR targets and fairness, which are very important business objectives, are put in jeopardy with selective labels if these labels are all assumed to be label positives and if we train models on this wrong data. So to wrap up, we propose the data bias taxonomy to characterize bias and relate to different fairness accuracy trade-offs. We modeled two scenarios of bias in performative prediction, strategic classification, and selective noise labels, and we show how these have detrimental, unpredictable, and unidentifiable effects on fairness and performance. I encourage you to check out the paper for more details on the experimental setup of each scenario and on the background of each experiment. And we hope that this work inspires future research on developing suitable fairness interventions for dynamic environments. Thank you very much.